Alrighty, so this is lesson 18, I think. I'm losing track, but it's another skill session. I'm going to do roughly 10 graphs here quickly, mostly mechanically, just for practice. And let's have at it, and hopefully it's a short video. Pause the video and you try to graph each of the functions that we're going to be looking at, and then check your work. See if you did it the same way, which is hopefully the easiest and quickest way. And if you find an easier or quicker one, throw it in the comments. We'll adopt it. My rule. So every test, every lesson set thus far has had a 0 and a 0 and a table. And so you cover up the y's, you get the x's, 77/3. You cover up the x's, you get 77/-5 or -77/5. That's called standard form. Standard form of the equation. If I don't see that, then you're not graphing according to standard form, and I don't know why. So you show those points. That's roughly what? Yeah. 3 goes into 60 20 times, so you got another 23, another 26, somewhere around 26. So an x value 26, somewhere out here, we'll call that 77. Well, I know, first off, it's a subtraction, so I know I'm going to be increasing. So I can put 77 thirds, gets me 0 for an altitude. And this goes what, 14, 15 times, so -15, and maybe right about here. And that would be 0, -77/5. So standard form is all about the x and y intercepts. It's nice if you put some arrows at the end so that you're not just graphing something like that, which is actually wrong. Okay, there's infinite number of solutions, and you want to show them all. Oh, I didn't bring Renee over. We'll have to go to the desks. All right, not going to take the time to even bring Renee over today. It's not that many problems. So now we got a linear function, and if you're able to plot some points, like 1 gets you 17, and then change your x's by 5, well, there's 3 locations. Go down 23, so 17, I believe, -6, I believe -29. Hope I did that right. And all you got to do is plot a couple of those places. 117, why don't we call that 117? Let's approximate. And let's do 6, -6. So if that's 1, 6, -6, maybe here, 6, -6, you're done. Oh, boy, I did pretty good that time. Did pretty well. So with these other functions, I think shape should be drawn first. I've noticed that some folks are having a little difficulty with plotting coordinates in the correct location. So maybe we should just do the x's. Let's find the x. -30 divided by twice the a term gives us a value of 5. So we now know that our x value is 5, and therefore our y-intercept is to the left. Maybe that'll correct some of the difficulties. Putting in a 5, 150. This better be -75. It is, and we got -4. Putting those 3 things together gets me 75 -4, which is 71. And I know I have the y-intercept already given. So that's good enough. If you want to put in 10 gets you -4, just so that you can see the symmetry, nothing wrong with that. But as soon as you give me the vertex and another point, I can't misdraw it. All right, so absolute value is somewhat similar. Instead of cup shape up or cup shape down, we either have V shape up or V shape down. And in this case, because that's positive, V shape up. Critical number is 3, so my y-intercept is to the left. Maybe that'll correct those difficulties. I can see a 4. What goes with a 0? Well, we got a little math to do. I believe 10. And 10 is bigger than 4, so that's a good thing. Therefore, 3, 0, so 6 gets me 10. And we got ourselves some nice symmetric points, vertex. You got the graph. What's the range of this graph? I think we ought to start talking about domain and range. Domain, all x values, all x's that are real. We'll just leave it like that for now. The range, well, I gotta have y values greater than or equal to 4. I don't think you're seeing anything below 4. So that's the range. What's the range of this one? Y values less than or equal to 71. What's the domain? Reals. Domain is reals. I think we ought to start doing that for every function now. So you understand domain and reals. All right, so I see a positive square root. So I'm going to get one or the other with an endpoint. This is a positive, so it's going up pretty quickly, given the kind of the chain rule effect here. But let's look at that coordinate. I think I'm looking at 1/2. And I think I'll throw in, well, what's a simple number here that I can get? Subtract 5. I like the square root of 25. I got 10s and 5s, so I think I might as well figure out what makes this thing act like that. So I got to add 5. Looks like I got to put a 3 in. Don't know why I couldn't see that immediately, but I didn't. The 3 gets me 25. Square root of 25, 5 times 4, 20 plus 7, 27. All right, and 1/2 gets me a 0. So 1/2 gets me the square root of 0 plus 4 times the square root of 0 plus 7. Looks like it gets me 7. So what makes a 0 is critical because that's the smallest square root you can have. Square roots of negatives are imaginary. We don't graph them on in the x, y coordinate, Descartes coordinate system. So what's the range? Y value is greater than or equal to 7. What's the domain? The domain is x's that are equal to, greater than or equal to 1/2. Okay, I can't plug in anything smaller than 1/2 in here. I can't plug in 0. That would give me the square root of -5. That's not going to show up on the xy plane. Okay, so there's your domain and range. All right, so mechanics for graphing exponentials. You work with the differentials. I got one differential of 5. I got one differential of 10. I know it's asymptotic behavior, so we'll do a dotted line. Y equals 2. It's already got my y values. 2 and 5 is 7, and 2 and 10 is 12. So now I'll erase these from the board, right? And so we've got doubling of differential. That's my first jump, provided I pick the right numbers, and I hope you can see 6 and 10. They're begging to be used. 6 minus 6, 0. That gives me 5 times 2 to the 0 plus 2. Well, that's 1. So I got 5 times 1 plus 2. That was the differential of 5. What made that happen? 6. I got a 12. What's going to make that happen? 10. And I got exponential growth. And I got a good graph, quick and easy. What's the range? You're pausing the video, I hope. Greater than 2. All my y values, bigger than 2. What would be a nice number to help you understand the asymptotic behavior over here? How about 2 to the -1 to the -4? No, let's times 5. Yeah, it doesn't matter. I said it. Is there an easy number with 5? Not coming to mind. So yeah, let's do -4. So when does x minus 6 over 4 equal -4? That's what you got to do in your brain. So minus 16 plus 6 is minus 10. So if I put minus 10 in here, I get minus 16 divided by 4, which is 2 to the -4, which is 1/16. Times 5. I hope you can see that's a very small fraction, little less than 1/2. So 5, so I'm at a very small fraction. I've got a jump that's a little less than 1/2 on top of 2, right? And what happens if all of a sudden it was 5 to the -5, or -6, or -8, or -10? Well, 5 to the 2 to the -10, excuse me, 2 to the -10 is 1 over 2 to the 10th. And I hope you can see that smaller differentials, cut in half, cut in half, cut in half, cut in half. Right? I'm cutting each of those differentials in half. And if you cut something in half, it eventually disappears. So we have a disappearing act as we move to the left on top of 2. That's not going to disappear. Doesn't matter what numbers I pick for x, that 2 is going to be there. All right, talking more than I thought I would. So we got another exponential function. Why not put in the growth e bigger than 1, right? And so I got another y equals 2. And I think my first jump's going to be 7. If I pick the right number, and I think the right number is still going to be 6, and I think I'm going to want a slightly different number for this, because I like the number 0 and I like 1.1 when I'm dealing with e. All right, so I got 4.4 plus 1, 4.4 plus 6, 10.4. Right, so 6 is going to get me 9, and 10.4 is going to get me approximately 21 units plus 2, 23. All right, so 7e to the 1.1 plus 2 is 7 times 3 plus 2. So we got our differential there, you know, the 1 3 times 7, a little bit differently than we did in the previous problem. It does require, you need to know that e to the 1.1 is approximately, for our purposes, 3. All right, number 56. Bring this table over a little bit. I'm missing Rene. All right, so logarithms are the inverse of the exponential. The inverse of a horizontal is a vertical asymptote. And I think I can see the numbers I want to play with here. I want 0, I want 1, and I want 4 in this parentheses. If I do, I get 5 log base 4 of 0 plus 6, which is undefined. Okay, and that means I need numbers bigger than 2. I need numbers bigger than 2. What happens when I put a 1 in there? Well, I do believe log base 4 of 1 is 0 times 5 plus 6. Sure looks like I'm always going to get that on step 2. I got a feeling I'm going to get 11 on step 3 when I change this to a 4. Oh, yeah. What do you put on top of 4 to get a 4? 1 times 5 plus. Oh, yeah, I'm seeing that. So there's your graph. We know we're going to get a 6. We know we're going to get an 11. Just by looking at it, if we pick the right numbers, what makes a 0? 2. What makes a 1? 9. What makes a 4? 30. So those are the numbers I want. I got the 2. Now I got the 9. Now I got the 30. Now I got the graph. The more times you do it, the quicker and easier it becomes, to the point where you can write these in under 10 seconds. Okay, I'm going to bring Rene over now. I'm close enough. I need my buddy. There we go. Come on, Rene. There we go. Now I'm happy. Let's put these over here. Get a nice perch. Let's go over here. Let's close this door. Anybody bothers me, I'll kick them out. All right. Oh, ln. I think I want to do one of those again. What makes a 0? 3. Okay, what am I going to get? I'm going to get a 7, and I'm going to get a 12. 5 plus 7. If I pick the right numbers, I want x minus 3 over 4 to equal 0. I want it to equal 1, and I want it to equal 3. Because I like the ln of 3. I like the ln of 3 a lot, because I know that's approximately 1.1. All right, so what makes, well, we already got that. When is this thing equal to 1? When I multiply it by 4 and add 3, 7 gets me 7. What makes it 3? 4 times 3 is 12, plus 3 is 15, and I believe I'm done. Understanding this would take a little bit of effort on your part. So what would be a nice number for ln? Well, why don't we do the ln of a third, which is approximately negative 1.1 times 5 is negative 5.5. plus 7 is positive 1.5. Okay, so where's 1.5? Well, it's certainly below 7. All right. And when is this thing equal to 1/3? Well, I got to multiply 1/3 by 4. 4/3 plus 3 is 9/3. So what did I say? I forgot what I said. Where was I? Oh, 1/3. So let's actually make sure everybody sees what's happening here. All right, so that's a 3. So I'm multiplying by 4 to that side. I'm adding 3, which is 9/3. So I've got 13/3. Okay, 13/3. Is that less than 7? Yes, 4 1/3. So let's do it this way. 4 1/3 gets me 1.5. All right, and what happens if it was 1/9 or 1/27? 1/81. More and more negative values, and my x's aren't changing a whole lot. Visually, from 1/3 to 1/9 on a number line, not seeing much change. 1/9 to 1/81, 1/81 to 1/343. You're not even seeing that visually. Okay, but the y values are going down by 5 each and every time. Okay, so what do I see? I see a 6x squared. That's a narrow parabola. I see a couple of points here that are going to be easy to work with. I can see x equals 3 is easy to work with, and -5. That gets me zeros. -5 on the left, 3 on the right. What's the number between -5 and 3? Add them up and divide by 2, and I think you get -1. 4 units, 4 units. Drop in a -1. -2, -6, -8, drop in a -1. +12, that looks like 80 and 16, -96. How far is it from -96 to 0? 96 units. How far is it from -1 to 3? 4 units squared is 16. And just coincidentally, that squared change into 96 is 6 to 1. Oh, what a coincidence. What a coincidence that the coefficient of that was 6x squared. And when I did that, when I did the 3 plus 1 squared change, -1 to 3, 4 units of change squared. Yeah, I get the number I want. When is y greater than or equal to 0? Well, we got the graph in front of us. Is there any reason we can't just look at this and go, oh, these y values are? When do I get those y values? When x is greater than 3. And when do I get these y values? Oh, when x is less than -5. And that's only true if you put the word or in there. Mathematicians, I don't want equal to. Mathematicians use interval notation. -infinity to -5, union 3 to infinity. Now, how does this problem change? Oh, I did say or equal to. Okay, so how does it change? Well, we just simply do that in this case, right? Less than or equal to -5. Yeah, I got to write that properly. But interval notation, you can't bound -infinity, but we use a bracket. A bracket shows colored in dot in this direction. Union bracket 3 works to infinity, and that's another closed circle. If it wasn't equal, then we'd have that shape from previous classes. I'm sure that's familiar to you. One more problem, then later this afternoon, probably early evening, I will do problems 1 through 48. Students in class have an A, a B, and a C problem in front of them, test tomorrow. And I've been tackling the C questions. And the C question on this one is 1 period, graph 1 period of the sine function. Remember what the sine function looks like? We're going to take a walk around the circumference, drawing triangles. What happens to the heights as I move around the first 90 degrees? They go up to what? To 1. and they go down to -1. And we get that one period of change before we start using numbers repetitively, finding numbers repetitively. Now, so this is really the sine and cosine function only kick out numbers between 1 and -1. So if I triple that, I'm cutting out numbers between 3. Now I'm going between 3 and -3. And that's the range of this particular function. I mean, I could have put +10. If I put +10, then I would have been going between 13 and negative what? -3 + 10, 7. Still 6 units of change. Okay, but right now there's no constant there. So I'm starting in the middle. So that's a 0. And that happens at 0, 0, 0. Now, normally one revolution occurs when we've traveled 2 pi radius lengths, 6.28 radius lengths around the circle. That's a radius. Radius length puts me about there, 1, puts me about there, 2, puts me about here, 3, so on and so forth. There's 6.28 radius lengths in any circle. So what makes 2 pi? Looks like pi does. Pi. Oh, sorry, 4 pi. Yeah, end of the video. Time to make mistakes. 4 pi divided by 2 gives me the first period, and that brings me back to 0. Okay, so we're slowly building up difficulty. The last test, I asked you just to graph the cosine curve, 1 period. Now we're looking at, and I think on a worksheet, the sine graph, 1 period. Now we played with the period of the function. Last thing I'll say is if you think of this as running around the track, and you're going half my speed, it's going to take you, I'm probably going half your speed. It's going to take me twice as long to go around the track. Okay? How long does it take the normal? It sounds like I'm giving the numbers human qualities. What's the period of the function? Typical sine and cosine 2 pi. If I'm dividing by 2, I need 4 pi to get 1 revolution. All right, that was well said, I think. All right, as Yasser would say, stay safe and warm. We're hoping it warms up here soon. All right, post this, and then 1 through 48 coming, or 1 through 48 coming your way later in the day.